All right, so now we're going to do some more hands-on applied stuff with logistic regression in R. As usual, there's a bunch of packages that you need to load, and if you get errors about any of them, you might need to install them. We are going to use the LM test package in this lab. So last lab, we had some logistic regression models. They were using this Wickham data, and I had mutated the data to make a new variable isAlive, which was a 1 or a 0, so that it would work well for logistic regression. So I had added that variable, and then I had two logistic regression models. One which was just a simple logistic regression with age as a predictor, and another one that had age and smoker as predictors. And we've looked at the summary of these models before and talked about interpreting the coefficients. So we could interpret this coefficient in the log odds space, or we could exponentiate it and interpret it in the odds space. So a 1-year increase in age would be associated with multiplying the odds by a factor of 0.885. So your odds of being alive are going to go down over time. So we've talked about those interpretations, but you might not have a ton of intuition about what happens when you change the direction or magnitude of the intercept coefficient or the slope coefficient. So one thing that I've done is I have made a Shiny app. So it's a little web app that is coded using R. It's going to allow you to experiment with changes to the intercept and slope coefficients. So when you open the app up, I think that it's automatically set to the actual coefficients from the model. And then I've got the probability space and the log odds space here. And then you can see what happens if you change the intercept and the slope. So I think the book explains what each of these coefficients does to the shape of the line in the probability space. But I think it's easier to see when you get to play with it yourself. So let's reduce the intercept of the line here. So of course in the linear regression space, we know what the intercept does, it just moves the line up or down. So I'm moving it down a little bit. But then I can see what's happening in the probability space. And maybe it's a little bit difficult to tell what's happening here, but the curve is just moving to the right and to the left. So it's the same curve, it's just getting slid back and forth. And I put it back to 7, okay? And then the slope, I could move it and make it slightly less steep if I wanted to, make it almost flat. I could make it a little bit positive. That's going off the plot for probability, so I don't think we're going to be able to see it here. But we could also make it a little bit more negative, and hopefully you can see what's happening to the curve in the probability space. It's becoming steeper. It's a quicker drop from 1 to 0. So instead of having that kind of slow drop in between, we're going very steeply between the two. And again, it looks a little bit weird in these spaces because I've plotted the data, and of course this isn't the model that really fits. But then hopefully that can show you how the intercept and slope affect the model. All right, so hopefully you now have a better understanding about how changes in the intercept term affect the shape of the logistic curve and how changes in the slope term affect the shape of the logistic curve. Let's talk a little bit about fitted values. So like with linear regression and ANOVA, we can find the fitted dot values, which are the sort of predictions for each of the data points. And if you just print these out in your console, you should be able to guess what space they're in. And it looks like they are in probability space because they're all between 0 and 1. So they're in the probability space, all between 0 and 1. And so we might want some fitted values to go along with our data so that we could, make some plots. And so we could use a mutate to add those fitted values to the original data, but we can use the broom package to just tidy up our model for us. And in order to do that, we run augment on the model object. I think I did this last lab. This time I'm going to include data equal Wickham. And if I control enter here, I'm going to get a new data set in my environment. And so let's do that. Control enter. I've got Wickham. It's got 1,314 observations of 10 variables. It's got the original 4 variables from the Wickham data set, and then it's got a .fitted column. Interestingly, these are obviously not probabilities. The fitted values that come with the augment are the log odds because they're things like 4.6 and negative 1.24. So it has all the original variables plus information from the model. Fitted values are in log odds space. And what does that data argument do? It brings along all variables in the original data set. So if we didn't include that, we would only get the variables that were used in making that model. Okay, so now that we have those fitted values, which are log odds, we might want to create odds and probability here. So I can mutate and make a new odds variable, which is the exp of the fitted values, and the probability, which is the odds over 1 plus the odds. And I can control enter here. Now I'm going to have even more variables here. I've got the odds and I've got the probability. So what does that mutate code do? It makes those two variables. And I could do the same kind of thing for my, my second model. So I'm going to augment the data, and then I'll mutate and make the odds and the probability there. And now that I have the log odds, the odds, and the probability, I could visualize my model in those 3 spaces. So I could look at the probability, and I think we did this last lab a little bit. I could also do it for the multiple logistic regression model. So I would have 2 lines, and that smoker term, if I look at that, get big, it looks like if I'm looking at the smokers, they are slightly less likely to be alive at every age point than the non-smokers. So these are sort of parallel lines, but of course they don't look exactly parallel in this probability space. So that probability plot, it can have the data points because it's in the right space, but once we move into odds, then we kind of lose that ability. So I could look at the plot of the simple logistic regression model. I could also look at the plot of the multiple logistic regression model, and again, we can see how those 2 parallel lines show up. And I could also look at the log odds space. It's going to be a straight line, or for the multiple logistic regression, it's 2 parallel lines. And the question is, why can't the odds and log odds plots have the data points? And the reason is because there's no way to convert a single data point into odds or log odds. So if we want to see some data points on those kinds of plots, we need to use binning. So this could be a way just to sort of plot some data in those spaces. It's also useful when you want to check the linearity of the logit. So we want to bin the explanatory variable and then compute the average proportion of the response within each one of those bins. So here's some code that's going to do that. I'm going to take my Wickham data, which has just 4 variables right now, and I'm going to create a new variable called age group. An age group is going to use the function cut, which is going to convert a numeric variable into a factor. It's going to divide the range of x into intervals and code the values in x according to which interval they fall in. So I'm going to cut age into 10 bins. So if I control enter here, Now I've got 5 variables. If I click on it, I can see this person, they're age 23, they're falling into the bin 17.9 to 24.6. So R has automatically found those 10 bins for me and has made this new variable. And then if I wanted to, I could take the Wickham data and then I could group by that categorical variable, and then I could skim whether or not they were alive. So let's Control Enter here. Maybe I'll make this a little wider and try that again. So what we might want to look at here is the mean, and that's the average of the is alive. That's basically the proportion who are alive in that category. So in the really young group, 98% of them are alive. And then in the next group, 98%. Now it's going to 96, 91, 80, 71, 61, 23, and 14. And then in that last group, none of them were alive. Everyone was dead in that older age range. All right. So now I want to take that data set, which has 1,314 observations, and then I want to make a little mini data set that just has 10 observations, one for each of those age groups. So I'm going to take the Wickham data, and then I'm going to group by age group. I'm going to summarize the mean of is alive. That's going to be the proportion that were alive in that age group. I'm going to make the mean of the age, which is just going to give me an average age for that bin. And then I'm going to do a mutate. I'm going to find the logit using the proportion, which is sort of like our observed p hat. So I'm going to do the p hat, 1 minus p hat, take the log of the whole thing. So let's try Control Enter here. And let's find that data set. Oh, it's the one with just 10 observations. So I've got my age group. I've got the proportion that are alive. So these should be the same numbers we saw in that skim a second ago. I've got the binned age, which is basically going to be the middle of the age bracket. It's not going to be exactly, because it'll be the average of the number of people that ended up in that bin. And then I've got the empirical logit. So I've got some numbers there. All right, so what does that code do? It comes up with the empirical logit. And how many observations? Just 10. So now we could see how that logistic curve fits through that series of points. So first we can do this in the probability space. So I'm going to take that binned data. I'm going to plot the points, the binned age against the binned alive. And then I'm going to add a geom line, which has a different data set. It has the log M1 data, and I'm going to plot the probability. So let's see how that looks. So this is sort of like the empirical probabilities. So I've got the binned age and the binned number alive, and it looks like that curve fits the data pretty well. But it's hard to tell. It's hard for me to know if these are really close to the line. So this is where the empirical logit comes in. So one of our conditions for logistic regression is we need the logit to be linear. And so what we could do to check that is we could look at the empirical logit. So I'm going to start with the similar data set. My x is my binned age, but my y is my empirical logit. And then I'm going to plot this against the fitted values, which remember from my augmented data set, those were the logits. So let's look at this. So this is the plot of the line in the log odds space, and these are my empirical logits. So I found the proportion that were alive in a particular age bin, and I found the log of that proportion over 1 minus the proportion, and those are my sort of data points. And now I can see if they look linear. And again, why can't we take the logit of the actual responses? Well, because our actual responses are either 1 or 0. And so we can't find an empirical logit for those numbers. We have to bin to get a proportion that we can use sort of like a probability. So we've got our three conditions. Independence and randomness are the thinking conditions. Linearity is the one where we can check it using the empirical logit plot. This is that same code again. And does it look like the linearity condition is upheld? Yeah, it looks pretty good to me. There's some stuff happening at the very beginning and end of the plot, but that sometimes happens just because of this sort of edge effect. And then let's just talk about assessing a logistic fit. We've talked about the G statistic. If we needed to, we could find the log likelihood of a particular model, but it's probably going to be more useful to just use the LR test for the likelihood ratio test. So if I control enter here, then I can see the output. This looks a lot like a nested F test, and it's going to give me a p-value of comparing the model that has a predictor to the one that just uses the mean. It gives you a p-value. It looks like this model, the simple logistic model, is better than just using a mean because we've got a nice significant p-value. We could also use a nested likelihood ratio test if we wanted to compare two models. So again, this is like ANOVA, M1, M2. This is going to be LR test of two logistic regression models, and it's going to tell me is model 2 better than model 1, and in this case we got a big p-value. No, it doesn't look like using smoker is better than just using age. So you could play around and try out some other models and try and figure out which one you think fits the data best. So we've already done a little bit of comparison to the null model using the likelihood ratio test just on a model by itself, but we can also do some comparisons that are a little bit more pencil and paper. So we often want to compare our predictions to the null model. So we could find the average, which is the mean of the number that are alive, and that's 72%. So we could use that average as our prediction. So for every single person, we could predict that they had a 72% chance of being alive. We would round up to 1, we'd predict they were alive, and we'd get our prediction right 72% of the time. So we want to do better than that with our model. We want to get the prediction right more than 72% of the time. We can do this by just classifying what our predictions would be. So I'm going to take my Wickham log M1, which is my augmented data set that has to do with the simple logistic regression model. Let's close some of these other ones. It's a little bit easier to get to that. And we're going to make a new variable called predict alive. And so if that probability, which was over here, if that probability is greater than 0.5, we're going to predict 1, that they're alive. And if it is less than or equal to 0.5, we're going to predict that they are dead. So if I control enter here and go back here, now I've got predict alive. So I predict these people are alive. I predict this person is dead because they had a probability of 0.22 of being alive. So now I've got predictions of alive or dead. And then I could take my data set, I could group by whether they were really alive and also whether we predicted they were alive. And then I could summarize n is equal to n open paren close paren. And so this is going to show me that there were people who were dead and we predicted were dead. We got 244 of those people. There were people who were alive and we predicted they were alive and we got 846 of those people. And then there were people who were dead and we predicted them alive, 125. Predicted who were alive but we predicted were dead, 99. So let's see how many we got that were correct. So we got 244 plus 846 were correct. So we got 1090 correct. And we got 125 plus 99, 244 incorrect. And so then are we doing better than just using the mean? Well, let's see. So we got 1090 correct out of 1090 plus 244. We got 82% right. Yes, we got 82% right. which is better than 72%. That's better than using just the mean. We could do the same thing with our log M2, our slightly more complex model, predict based on the probability, and we could group by them being alive and look at this one. And then we could see how many we're getting correct. So we've got 251 correct plus 851, and this is going to be out of the full 1314. Looks like we're getting 84%. So we're getting 84% correct. Do we think that that's better than our previous model, which was 82%? It's a little bit better, but is it significantly better? It's not clear. And that kind of agrees with the results from our likelihood ratio test, where it said it wasn't really significant. It wasn't a lot better. So yes, it does. All right. And then I just have one more thing that I want to show you, which is a little bit more of a sophisticated method for assessing the quality of the fit. We can look at this thing called the C statistic. C stands for concordance. And the idea is we're going to pair up a success with a failure, and then we're going to compute whether the fitted probability of the success was greater than the fitted probability for the failure. And then the percentage of pairs that satisfy that are kind of our C statistic. So we're going to use this function rcorsens, which comes from the hmisc package. Hmisc is, let's see, hmisc is this Harrell miscellaneous package, which is by this person named Frank Harrell, and he made the package for just miscellaneous things that he liked using. So it's kind of a hodgepodge package, and I've found that it has a lot of conflicts with other packages. So instead of doing library hmisc and loading in all of the functions that come with hmisc, I'm recommending that you just use hmisc : and then the name of the function. And this is a way to use a function without actually loading in the whole package. So let's see, what was I talking about? The concordance. Even if your model has no predictive power, it's going to be right about half the time, just because there's only, it's like 50-50, flipping a coin, you could get it right. So let's just make a couple random numbers. So we're going to make a little data frame called X, which has some random numbers in A and some random numbers in B. And then if I run the concordance for this these two random numbers, I'm going to get a C statistic of about 0.5. So we really want a number that is significantly bigger than 0.5. So again, I could run this on my true is alive against my fitted values from the log M1. Remember, those are in terms of probability. And my data is going to be Wickham. So if I control enter here, I'm getting a C statistic that's quite a bit bigger than 0.5. And again, this is telling me that this model is better than the mean. So that's my last way of assessing a logistic regression model. So this whole lab has really been about different ways to assess whether a model is good if it's a logistic regression model. So we've talked about checking the conditions, looking at plots, interpreting some coefficients a little bit, and then doing things like likelihood ratio tests so that we could see if a model is better than the mean or if it is better than another model.